Okay, so in this video we'll talk about Eulerian graphs, and before we do so though, I want to play a little game with you, something you may have seen before in other contexts, or maybe even as a kid. So you have some pictures here on this slide, and get out a piece of paper, get a pen or a pencil. Try drawing these graphs without lifting your pen and return to the starting position, right? So are you able to basically draw the graph in one go without lifting your pen from the paper? So pause it right now if you want and try it out. So were you able to? Were you able to draw these graphs without lifting your pen, or maybe just a subset of these graphs? You probably try the first one and then saw that, hey, I could actually draw it without lifting my pen, but I don't return to where I started. Right? So it's kind of cheating there. Well, not really, right? We don't satisfy the second condition, but we do satisfy the first condition here. For the second graph here, well, for this picture, you can try something like this. Maybe it goes here, down, here, and you're stuck. Right? You're still missing this line. And you don't return to where you started, which is this vertex. Right? So you can't do it here, and you can't do it here. But for this graph on the right, you can actually do it. Let's see, maybe you did it this way. This, and then go here. Okay, so it's not like, okay, let me do that again. Oops. There. Oh, so it's connected here, but yeah, you got the picture. Here you can actually do it. And it turns out that there's a nice characterization of graphs for which you are able to do this. And so in fact, let's define what it is we're doing first. What we just drew there is called an Eulerian trail. And it means basically that there is a trail on your graph that contains all your edges. Okay, so what is a trail? A trail is simply an alternating list of vertices and edges, basically telling you which vertices you're visiting when you're walking along these edges. So for instance, this is a trail. So let's label the edges here. I'll use numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So an example of a trail is, say, 1, 3, 4, 6, 5, 3, 2. So I can write that as 1, and then you have the edge 1, 3, and then you have the vertex 3 and the edge 3, 4. Right? It's an alternating list of vertices and edges. Now, we won't always have to write the edges in between. I mean, I could just be writing 1, 3, 4, 6, 5, 3, 2 instead. Because for this specific graph, it's a simple graph. And what does simple mean? It means between any two vertices, there's at most one edge. So there's no ambiguity. When I say vertex 1, you go to vertex 3, it has to use this edge between 1 and 3. Right? So sometimes if you have a multigraph where you have multiple edges in between two vertices, sometimes it's helpful to specify what edge you're actually using in that trail. And the reason for that, why we're so concerned with these edges, is because you cannot repeat edges in your trail. Right? So this is a trail because none of these edges were repeated. It's not a closed trail because you don't end where you started. But if I had just continued on to 1 from 2, then it would be a closed trail. Okay, what does this have to do with our graphs here? Well, essentially what we're doing is we're trying to draw a trail on these graphs such that we contain all the edges in this trail. Right, so this trail here, 1, 3, 4, 6, 5, 3, 2, 1, is not an Eulerian trail. Right, so Euler here, famous mathematician, that's what this concept is named after. That's who this concept is named after. Can we find an Eulerian trail on this graph? Well, I already demonstrated one to you on the previous slide, right? When I showed you that we are able to draw this graph without lifting your pen. So maybe we could do 1, 3, 4, 6, 8, 7, 6, 5, 7, 9, 2, 5, 3, 2, 1. Okay, so that's 1. So 1, 3, 4, 6, 8, 7, 6, 5, 7, 9, 2, 5, 3, 2, 1. And this is not an Eulerian trail. So note that we don't repeat any edges. But then it is a closed trail because we end where we started at vertex 1. And we're able to draw the graph without lifting our pen. So this condition here really is the same question as, does the graph have an Eulerian trail? And we do have a name for these graphs, as you see here. We just say that the graph is Eulerian. So this graph is an Eulerian graph. So naturally the question is, how can we tell that a graph is Eulerian? What characteristics does the graph have to satisfy so that we're able to do this? Now again, if you go to the previous page, what separates this graph on the right from the two graphs here on the left? And in fact, what distinguishes the first graph from the second? Because you're able to draw something similar for the first graph, where it's not a closed trail. So, can you think about it? I mean, there is one simple condition that you need, in addition to another one, right? There are two. And if you've been reading the course notes, you would have seen that theorem as well. First condition you need is that the graph has to be a connected graph. And what connectedness means here, what a connected graph is really self-explanatory from the name. Connected basically means from any vertex on your graph, you can walk along the edges to get to any other vertex on your graph. Okay, what does that mean? It means that the graph that looks like this, let's say if you take this thing as the graph G, then it's not connected, right? Or we also say it's a disconnected graph. Because from this vertex, for instance, 1, and this vertex, I'll call it 4, there's no path in the graph that takes me from 1 to 4. And now, be careful about these terms, right? Some of these graph theory terms, like connected, trail, path, they mean something in English. But in graph theory, they mean something very specific. And as you can see here, the definition of a path is that it is a trail, right? In the sense that it is also an alternating list of vertices and edges, where if it's a simple graph, we can just write what the vertices are. But aside from the fact that no edges are repeated, no vertices are repeated as well. Right, so just to make that distinction clear here, just going to draw something here. Okay, so something like this maybe. 1, 2, 3, 4, 5, 6, and 7, and 8. So I could say that we have a trail 1, 2, 5, 8, 7, 5, 4. Right? It's not a closed trail, but it is a trail because you're not repeating any edges here. It's not a path though, because the vertex 5 appears twice. A path cannot repeat vertices, so a path would be something like 1, 5, 7, 8, 6, 3. Right? That's a path. Since you're not repeating any vertices, then you're not repeating any edges as well. And this is what we use to tell whether a graph is connected. Like if you can check from our second graph here, I can give you any two vertices. I can say, well, that u equals 5 and v equals 3. Is there a path from 5 to 3? And I can say, yes, there is. 5, 6, 3 is a path. And what makes a graph connected is if I can give you any two vertices, and there's always going to be a path between them. Okay, and that's the first condition that can help make a graph Eulerian. It has to be connected in the first place for you to be able to draw it without lifting your pen. And now that sounds really obvious when I say it out loud, right? But we formalized it in terms of our graph theory definitions here. What's the second condition? It turns out that the other condition, so this is what I was talking about before, G is connected. The other condition actually has something to do with the degrees of your vertices. Right, so remember what the degree is. It's just the number of edges incident to that vertex. So how did I number this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now the degrees of each vertex are degree of 1 is 2, because you have 2 edges there. Degree of 2 is 4. Degree of 9 is 2. It's 4. It's 2. It's 4. 4. 4 and 2. So the degree sequence here is, well, a bunch of 4s and a bunch of 2s, so I'm not going to write that down anymore, but you can check. They're all even. And what this result says is that because they're all even, then you are able to draw without lifting your pen. It is Eulerian. And now look at these graphs, right? If I put my vertices here, so there are vertices there on the crossings. This is a 3. 3, 3, 4, 4, 3, 2. So it's not Eulerian. You can't draw it without lifting your pen and returning to where you started. How about the first graph? Degrees are 2, 4, 4, 4, and then you have 3s here. So you can't do it. The idea behind that result is the following. So I'm not going to prove it here formally, but the idea is this even condition basically it allows you to decompose G into what we call cycles. So we haven't really defined cycles yet, right? But a cycle is basically a path that's closed, right? So it's a path where you start and end at the same vertex. So this is the cycle of length 4, for instance. 1, 2, 3, 4, 1. And what's happening with this graph is I can actually draw it in this way where, okay, so one way of decomposing into cycles is this. There's a cycle here. There's a cycle here. And there's a cycle here. Right, that's the same graph. But now I've drawn it as the union of two triangles and a rectangle. What is it about cycles that relates to this even condition? Well, if you look at the cycle, each vertex contributes a degree of 2 to the whole graph. Right? The cycle adds 2 to the degree of each vertex in that cycle. That's why this vertex up here has degree 4, because there are 2 cycles passing through that vertex. And what about cycles allows us to draw this graph without lifting our pen? Well, I can do it this way. I can go through each cycle, and at some point where I intersect another cycle, I can continue drawing there, right? So I'll show you here in this graph. I can draw the red cycle, and at this point, oh, there's another cycle there. So I'm gonna follow the black cycle until I return here, and then continue the red cycle. Oh, and at that point, I do the blue one, and then return back. So you're basically inserting cycles within other cycles in order to draw the graph. So try playing around with this. There are multiple ways, usually, right, in general, to decompose a graph into cycles. Right? You can probably already see from this graph here that maybe there's another way of doing it. But try playing around with this condition, right, and convince yourself that this condition really is all that you need in order to conclude that the graph is Eulerian.